All right, I think we'll get started. Welcome in from the cookie and coffee area. Yeah, thanks everyone for coming. Got a bright light. So welcome to this joint MQ-REL seminar. We're pleased to have Daniel Argüeso here. And well, welcome back. He's been visited here several times since 2008. So yeah, good to have you back. So Daniel got his PhD in physics from Granada in Spain. And then he did postdoc stints in Hawaii and Australia at the University of New South Wales. And now he is associate professor at the University of the Balearic Islands in Mallorca. And his expertise covers mesoscale processes, extremes, climate change, extreme heat, and urban climate. And today he's going to talk about the infamous Cyclone Daniel in the Med. So over to you. Thank you.
Okay, can you hear me? Yeah? Okay, thank you for having me. It's always a pleasure to come to Ankara, talking to longtime colleagues and discussing some science. So yeah, thank you for having me. I'm going to actually divide my talk in two parts. One is going to be about Cyclone Daniel itself, and the other one is going to be a little bit of an overview of what we're doing now, latest thing that we were doing in the group. But the main thing is going to be about Daniel. Yeah, it's kind of funny because I've always thought when I saw hurricanes and these kind of things, how would someone feel if they put the name after you? And there we go, Cyclone Daniel. Yeah, so first of all, I will give you some background on the storm. The storm generated from a pattern that is very common in this area is an omega block with two main areas of intense rain, one in the Iberian Peninsula and the other one in the Eastern Mediterranean, in this case, the Greece, and then often warm conditions in Central Europe. So this is probably the situation that generates most of the extreme events, at least in the Iberian Peninsula when we studied there. Actually, this was a situation yesterday as forecasted by our in-house model, the TRAM model, which is a triangle-based model. And it's very similar to what we had in that case. You don't always get extreme precipitation when you get this pattern, but every time you get intense precipitation, it's something similar to this. That one actually is creating a lot of intense rainfall in Spain at the moment, yesterday and today. But now we're going to focus on the other part, on the other leg of this omega block. And that generated a cyclone that had some characteristics of a tropical cyclone, tropical-like cyclone called Medicane. This term was coined, I think, by Carey Emanuel a few years ago now. And it's not really a tropical cyclone, but it has some features that shared with tropical cyclones. I will discuss a little bit on that later. Here I've got some satellite footage of the cyclone landfalling in Libya, and we can see how it has some features that resemble a tropical cyclone. The term is actually a bit controversial because it's fuzzy. It's hard to determine whether an event is actually a Medicane. There's some of them that are very clear. This is one of the iconic Medicanes. It's often used as an example because it's very clear the shape it has, and then when you go into the structure of the storm, it's a clear Medicane. It's Llanos in 2020, I think. Same area of Storm Daniel, but they're not always like that. There are lots of them that are less clear to be a Medicane or a tropical-like cyclone. So what are they? What are these cyclones? Well, they're systems that have some features. I enumerate a few of them here, not all of them. There are some other as well. So most of the cyclones don't have all of these features, but only some of them. They have some symmetrical structure and a clearly visible cyclone eye. They have a warm core, most of the time quite shallow. They have some upper tropospheric outflow, convection and latent heat release, and it has rain bands and no frontal structure. This is when the medicane is already formed. But we must say that these systems are coming usually from a baroclinic disturbance. So in their origin, they might have very different characteristics. They're much smaller in size than tropical cyclones. And while they need warm temperatures to develop and to intensify, they don't need as warm temperatures as tropical cyclones to grow. They tend to happen between September and January. That's when the Mediterranean is warmer and provide more energy to the system, and mostly in two regions. One in the Western Mediterranean, north of the Balearic Islands, around France and Spain. That's where we come from. And the other one is around Ionic Sea. This is the area that we're going to look into today, to the Eastern Mediterranean. And they have very large impacts. And the main reason for that is that the Mediterranean basin is surrounded by lots of topography, and there are lots of people living on those slopes and near the coast. So every time we have one system of this kind, they tend to have lots of impacts in the region. And was Daniel a medicane? Well, here I show a couple of hard diagrams to show you that it it incurred in that area of tropical cyclone characteristics with a shallow warm core. We cannot compare these to tropical cyclones because, as I said, they're much weaker features than tropical cyclones, but it does have these features that resemble a tropical cyclone, like a symmetric warm core and in this case, relatively shallow. This one was very interesting because it generated a lot of rainfall in different regions of the Mediterranean, in Greece, other countries around Greece, Bulgaria, Turkey, and also in the southern shores of the Mediterranean, particularly in Libya. In both shores, we got record-breaking rainfall at daily and sub-daily timescales. And then, as I said, they had some of these characteristics of tropical-like cyclones. It had two phases, as I said. One in the northern part. In that part, it wasn't really a medicane yet. It was just a cyclone. Where it generated huge amount of rains in a relatively small area. For example, in Zagora, we had more than 750 millimeters in 18 hours. Some of these stations got over 850 millimeters, but then most of the stations stopped working after a while. So probably the accumulated rainfall in some of these stations was much larger than we actually could record. But yeah, so the rates were very intense, and this one in particular was a national record in Greece. This was the first part from the 4th to the 7th of September. Then we had the second part that hit Libya. In Libya, we also had a national record. We had over 400 millimeters in 24 hours. That was, again, the national record of Libya. And because of the way it hit this region, it was the deadliest storm in recorded history, both in Africa and in the Mediterranean. It was nearly 6,000 confirmed people died in this storm, and many other thousand disappeared or displaced. It's still not clear how many people died out of this storm. Here I can show you the floodings in the desert. Some lakes that formed right after the storm that were massive in that region. But the reason why so many people died here was not just the rain, which was much stronger in Greece, but because two dams collapsed. So this is the city of Derna in the north of Libya, and there were two dams that collapsed, and that was a major failure to kill most of these people. Okay, so what happened? What was the environment that helped to generate this storm? Well, the first thing we think of is the SST. If we look at the SST in the months before the storm, actually, up to now, we have huge anomalies of SST in most of the Mediterranean. 1 month before the storm, it was in some points up to 5.5 degrees above the normal. So it's really, really warm. It's still warm today. But as I said, the weeks before the storm, it was very warm. So our question was, what was the role of the local SST in intensifying the storm? Or at least what was the contribution to the rainfall rates that we observed? And so to do that, we designed a couple of experiments. I will go first and explain the control one. So we ran a few experiments with WRF at 3 kilometers. This is the domain we used. At 3 kilometers, and the first experiment, the control run, is just driven by aerophile, both in the atmosphere and the ocean. And what we did is run 16 ensembles that they were initialized 30 hours apart, from the 22 August to the 9 of September. So we can kind of take into account the dependence from the initial conditions. So remove that dependence somehow. And also get an ensemble so we can get some statistical significance out of the results. Here I highlight the 2 regions I'll be talking about. We focus on Greece and Libya because they were the 2 most hit regions. So before I jump into the second experiment and how we tested this hypothesis, I'd like to show you a little bit of the model performance for this event. So first, these are data from the National Observatory in Athens. Unfortunately, we don't have the time series. It's just accumulated over the entire period. Some of them, as I said, stopped recording, so they're probably higher than this. And I show them as crosses in this swan plot. And then all the points that I show here add model estimates. And I give here a schematic. So for any station, I get the 9 surrounding points, and I get all the ensembles that were initialized before the storm. So here we've got all the ensembles that I showed, that we use for this plot. And we see that overall, despite the huge amount of rainfall that we got, the model is actually capturing most of them. It's actually giving a good overview of the rainfall rates that we got in this region. Then we did the same for Libya. In Libya, it was harder because we were scrapping information from reports. So this is very qualitative. We got some information in different publications, but none of them were official. So this is just to give an idea of what happens in Libya, but we should be careful with this data. And also because we didn't know exactly where they were taking, we took 16 points instead of 9 points around the area where we were located the stations. And we have a similar behavior. The model is mostly underestimating these rates, but is otherwise capturing rates that are very, very big. The other reason for this difference is that most of the models are starting long before the storms arrived in Libya. So that might be one of the reasons why there is a difference, as I'll show later on. We also wanted to look at what's the spatial pattern of rainfall. So we compare with satellite-derived products. We know that they're not great at capturing extremes, and the aim wasn't really looking at the amounts generated, but rather looking at whether the model was able to capture these spatial patterns and the structure of rainfall in the region. And we think that it does a pretty good job in capturing this location of the rainfall cells, especially around Thessaly and Peloponnese, which is the area. Which is the area where we've got the maximum in Greece. Okay, so the second part, the second set of experiments is exactly the same. The only thing is that we modified the SST. And I won't get into much detail because it will make the talk very long, but what we did, or what a colleague of ours that are also co-authors of this study did, is estimating the distribution of the SST in each grid point and how it behaves with respect to the global near surface temperature. And so as it evolves in time, we have a variation of this distribution of the probability of the SST, and then they calculated what will be those distributions by removing the global warming signal. And that way we get a counterfactual SST. And we did exactly the same number of experiments, just with a different SST. I would like to show you the fact that we kept the atmosphere in the same way. So the boundary conditions and the initial conditions are just the same. The differences are coming essentially from the SST. We also did some experiments doing some sort of a pseudo warming looking backwards and modifying the atmosphere as well, but essentially most of the effects were coming from the SST and not the atmosphere. Okay, so in terms of what does mean in terms of the SST for this event? This is the SST, how it looked like at the beginning of the storm, the beginning of September, in the control run, in the counterfactual run, and the difference between the two. So obviously, in the counterfactual is a bit cooler than in the control run, something around 2 degrees, which is consistent with the trends that we've been observing in the Mediterranean as a whole. So we compare the two simulations, and here I compare the ensemble means, and I compare the rainfall for the September, just September. So we removed everything from August because we have only a few ensembles there. And we compare the difference in the spatial patterns of precipitation between the two, and we get these differences. All the dots are areas where the differences are not significant, and the other ones are significant. And what we get is that just looking at the domain average, we have a difference in rain that is about 42%. So by modifying the SST, we get 42% less rain in the counterfactual ensemble than the other one. There is a stark difference between the two regions. So in Greece, we've got only a difference in 17%, while in Libya, the difference is 81%. And I'll show you a little bit why we think is that. If we look at the time series, and in this case, as I said, unfortunately, we don't have the station's time series, so we use the satellite-derived products to get an idea of the evolution of the rainfall in the region. And first, we look into a big domain in central Mediterranean that it covers the entire storm, and we look at the different observations that are the dotted lines. Then we have the ensemble, there is the green line, the black line, and all the members in dots, varying in color from blue, which are the earliest one, till the purple, which are the ones that are initialized later on. And here is just bars of individual members to see when the peaks happen for each of them. So what happens if we compare these with the counterfactual? And we did the same. We compare with the counterfactual. The dotted line are, of course, the same because they're both coming from observations. But we can see that there is a drastic reduction in precipitation overall in the domain. This is the 42% I was mentioning before. Not exactly, because here we're not taking the whole domain. We're taking just an area inside, but it's kind of similar. And we see in the right-hand side panel that basically all the members, when we compare one by one, they all give a decrease in precipitation. So it's very robust across all members. And there we've got the comparison between the two ensemble means and all the members for the two runs. And we see this difference in precipitation basically during the entire storm, but mostly at the end of the storm. Then the same, if we look at the two regions that I mentioned, I just show here the differences. The scale is different because in Libya, the observations gave a huge amount of precipitation at the very end. There was a peak for one of the data sets. So that's the reason why the scales are different. But we see that for Greece, the difference is not as clear when we look at that region. When we move to Libya, that's when we see most of the differences. And there can be many reasons for this. One is that, as I said, it's happening later on in the simulations, but there are also the fact, as I will go through later, that the storm develops in the Mediterranean, but before it was going to Greece and it goes into the Mediterranean, it grabs some energy and moisture from the ocean, and then it continues to Libya. So if we modify the SST, it will mostly affect the precipitation in the second phase. So this is in terms of mean precipitation, but what happens to the extremes? And we're looking to the hourly extremes for the two regions, again for Greece and Libya. we extracted upper percentiles of hourly rainfall for each of the members. And here I've got 2 columns for each of the percentiles. One is a control and the other one is a counterfactual. And as a summary here, what we saw is that in Greece, we had a small difference between the two, although it's still between -20 to 5% in these 2 top extremes. But then if we go to Libya for the same 2 top upper percentiles, we get from -90 to -40 decrease in extremes. If we pick the top 10 events from all, from the region, from the entire region, from all ensembles, and we make this box plot, what we see is that the median in Greece is only decreasing by 5%, but when we go to Libya is about 50%, the difference in this top event. And this is important because those are the events that are actually causing most of the damage in the region. Okay, so we wanted to understand why we have this difference between the 2 regions. And as I said, there's some experimental design that might affect these, but there's also something related to the fact that the first part is not feeding from the Mediterranean. And to prove that, what we did is use a backtracking algorithm to look for sources of rainfall in these 2 regions. We look at the precipitation of Greece from the 3rd to 9th September, and then in Libya from 7th to 12th. And we backtrack the precipitation that fell in those areas back to 22 August and look where it was generated. We use ERA 5 for that. And again, we know that ERA 5 is not great for extremes, but the aim for this is to get an idea of the percentage of the moisture that was getting there and precipitating. So not so much the amount, but the percentage of rainfall that where it was coming from. But anyway, when we look at the amounts, ERA 5 is saying for Greece, for example, there are points where it's about 600 millimeters, 700 millimeters. So it's not far from observations. In Libya, it's a bit lower. It's something like 200. So it's a bit lower than Greece. And what we get here is, okay, I'll try to explain this map. Here we've got the solid black line, which are the 2 regions that we are looking at, the dashed line, which is the domain of our simulation, and then this is the domain we use to track back all the moisture. And what we get when we look at Greece is that we were able to track back 85%, roughly 85% of the moisture. And of that 85% that we tracked, 53 was coming within the domain, within our model domain. And only 36% was coming from the ocean, from areas where we could modify the SST. So that's the maximum potential we actually could modify from rainfall, because if we're modifying SST and basically coming from evaporation from those regions, so this is the maximum that we could really modify. If we take into account our ocean areas, it's around 56% for the Greek phase. But if we go to Libya, it's quite different because, well, we could track a bit more of the moisture. Within the domain is around 68%, but when we look at the local SST contribution to the rainfall in Libya, it's about 60%. So it's a lot of the moisture that generated the event here was coming from areas where we could modify the SST in our model. So if we reduce the SST in those areas, we're very likely to modify rainfall in much larger amounts. Okay, so I'd like to talk a little bit about the surface enthalpy fluxes and how this modification affects in this area. And if we look at the difference between the 2 simulations and look at the surface enthalpy fluxes, which are the key factor to invigorate cyclones in this region, especially tropical-like cyclones, we get that the difference between the 2 is quite big, especially in the area where the storm was brewing or was becoming a tropical-like cyclone. So this is directly affecting the storm as it was passing through that region. And actually, if we look at the division between surface latent heat flux and sensible heat flux, this is mostly latent heat flux. It's about 80% is coming from from heat flux. And then, of course, that has an impact on the amount of water that we have able to precipitate later. And this is what I show here, that over Greece, there isn't a big difference in precipitable water, but when we look at the area just before it made landfall in Libya, the difference is quite marked. So by modifying the temperature, we have an important impact in this region. Then if we look at other features of the storm, not just rainfall, and we look into mean sea level differences and wind differences, and of course, if we look at this again from a perspective of tropical cyclones, the differences are not very big. But for a storm of this kind, these differences are quite marked. Here we've got a lot of areas where the difference is around 2 hectopascals between the two experiments, and you could see that it follows very well the area where the cyclone was going. And then if we look at the differences in maximum wind over the region, this is maximum wind of the entire storm, we see that we get areas that goes up to 5 meters per second, which again, for this kind of storms is quite large. And what about, so we see this how it follows the track and the area, but what about from a perspective of the storm itself? And for that, we look into the tracks and the mean sea level pressure, the minimum mean sea level pressure for the storm. And here I show a couple of observations, these estimations from the Met Office. And what we get is that the track is quite similar to the observed one, so it's doing a good job in that sense. But what we get is that the counterfactual, basically all systems in the counterfactual, using the tracking algorithm we use to track the center of the storm, they didn't actually make landfall. They dissipated before it got to the land. All the blue ones, which are the control ones, they all made landfall in different areas of Libya, but they all made landfall around the same time. And it was roughly consistent with the Met Office estimates. The other plot is the mean sea level pressure minimum for the system. And here again, I show some estimations from the same source. And what we get when we modify the SST is that the storm doesn't get this minimum in mean sea level pressure that we observe in the observations and what we get in the control run. They're not as close as or as low as the observations, but we get deep values for the storm in this second phase. We've got one event, one ensemble member from the counterfactual that goes to those values, but it's the one that is initialized when the storm was already landfalling. So it makes sense that we still have those values because it was initialized with year 5 right before the storm made landfall. So we here see that it's not just about the precipitation, but also the intensity of the storm was quite different between the two. Okay, so I'll finish with this part. I'll make some conclusions about this Storm Daniel study. We saw that the total domain rainfall was significantly reduced, 42% over the domain. We saw that mean rainfall was in the Greek phase was largely driven by either the atmosphere or the remote SST. That means coming from the boundary conditions. And in the Libyan phase, it was strongly influenced by the local SST. So SST that we were actually modifying SST in the Mediterranean. And that's why we saw that difference between the two. Also, the role of SST on the extreme was very different between the two. We have a substantial impact on extreme rainfall in Libya, and then a limited impact on Greece. It's still reducing rainfall over Greece when we reduced the SST, but it was much more limited in the second phase. And now we're exploring, and that's one of the reasons why I came here, we're exploring other approaches. And the main one is using MPAS to remove the dependence from the boundary conditions. As I said, a lot of the influence from the first phase was coming from the boundary conditions. So our hypothesis is that we use MPAS and we modify the temperature everywhere in the domain, then we will only have dependence from the initial conditions in our system. Still strong dependence because the initial conditions are in present climate, but we could approach the problem from a different perspective. Okay, so I'll move to my second part, and it's about extreme rainfall studies in Western Mediterranean. So moving to the other part of the omega block that I showed before. And the reason for studying these, obviously, is the region that affect our institution area, and so we're interested for that reason, but also there are some scientific reasons for this. And the main one, and this is a plot from IPCC, it is identified as one of the regions with more uncertainty in what's happening with extremes in that region and what will happen in the future with extremes. The second one is a very torrential area in the sense that lots of the rain coming in the form of very short and very intense rainfall events. So it's interesting to look at this because it's not only a source of impact, but also a source of water for many of these regions. So it's interesting to look at them in these two perspectives. So as I said, they usually come in this form. And when you look at historical floods and historical events in the Iberian Peninsula and the Western Mediterranean more generally, what you get is very often something like this, which is very similar to what we saw before. And so you actually get a similar pattern around Greece. This is a paradigmatic case because this was the case that we saw 6 months ago in October 2024. There was the record rainfalls in eastern Spain. And I'll show this system here that was anchored in the topography in eastern Spain, and it generated crazy amounts of rainfall there. Actually, as I'll show later, it killed more than 200 people in that region, and we saw records at many different frequencies broken in that event, going from 10 minutes to 12 hours. The 12-hour record was close to be broken, but still the one in 87 stands, which is right above 800 millimeters. We were looking at different simulations. We're not very deep into the analysis, but I'd like to show you a couple of simulations that we made for this event. One of the reasons for this is that there was a lot of controversy whether they were forecasted and whether we could anticipate what was happening. And the fact is that it was very well forecasted. There are other systems like these that are harder to forecast in the region, but this one in particular was very well forecasted. And the models do a quite good job considering the amount of rainfall that we got in this event. And here I just show two cases, one using WRF at 2 kilometers, and we got these three cells, main cell. The one at the bottom is not very intense. This is what we saw in reality, but especially this one around Valencia region, where we got this maximum of almost 800 millimeters in 24 hours. And the model gives us a maximum almost right in the right position of around 600 millimeters in this region. We have to think that this amount of rainfall are really hard to capture with this model. So the fact that the model is generating this is telling two things. One is that the ERA5, of course, is providing very good information to the model, but the second one is that the model is able to reproduce not just the location, but the amounts. We often see that these simulations on these rainfall rates are very underestimated. In this case, we're getting closer to the observation. So far, it was almost 800 millimeters, but the idea is that we're getting there. If we look into EMPAS, which was our second incursion in EMPAS simulations, here with convection-permitting street, we get around 400 millimeters in that area, although the maximum is lower, is to the south of the Iberian Peninsula. We played around with the mesoscale reference, and then we get the maximum located where we observed it, which was this Valencia region, and there we get about 400 millimeters in 24 hours, which considering is 3 kilometers resolution is not bad. We should get closer to the actual rates, but it's not bad. Okay, so I'll this is an introduction of what kind of extreme events we're looking here, and I'd like to give you a climatological view on these extremes, or at least a climatological introduction to then show what we're doing right now. So starting from these kind of events, of course, this was last year, but this started a bit before, fundamentally inspired by similar cases. We do a set of experiments with WRF. 2 experiments of 10 years at 2 kilometers with a relatively large area. This is something like 2.5 thousand kilometers in the horizontal, in the longitude, and about 2,000 south-north. We provided RFI for the control run, and then we ran also a future run. 10 years, also 2 kilometers, everything exactly the same, except that we got the climate change signal from 27 GCMs, from CIMIP 5, and then we drove the model with those PGW boundary conditions for all variables, not just moisture, which is sometimes what people do with these. We did all variables fed into the model. We modified it with PGW. In both cases, we do explicit convection, and we get out precipitation every 10 minutes. That's the information that we get from stations. So the aim was to compare with observations at some later point. So that's why we got 10 minutes output. And so first, I'd like to show you something that I think is quite interesting. This is the distribution of precipitation over the coastal region. And I say coastal region because those are the areas where we get most of the extremes and the areas we're particularly interested in. And we look into present and future, which is the top one. We've got the solid line is the present, and the other one is the future one. The dashed line is the future. For 10 minutes, for 1 minute, and for daily. And we see an increase mostly at shorter timescales for these events. We also get something for daily, but it's not as clear as for the other two frequencies, which I think is interesting because it means that at scales that we often don't look at because we don't have the information, there is an increase in precipitation. But interesting enough is if we look at the values that we have here at the maximum for the present, which might seem very high, and we compare to what we got for the Valencia case, what we get, and this is the star that we got here, and I put it here because it happened in fall, and the orange line is in fall. What we get is that it's very consistent, the maximum amounts that we got for this record with what we get with the model. So these amounts are not crazy, and especially considering that we have the whole Western Basin, so much bigger area, then it's telling us that there's something physically very robust in these simulations when we compare to observations. If we go to compare with the Italian maximum, which is a continental maximum above 800 millimeters in the region, that was something like 5 years ago, we get also values that are very similar to these. So it's telling us that the maximum that we get in the model are very close to the maximum that we get in the observations. Yeah, and here it's showing those maximums. Okay, so with this in mind, we thought, let's look at how the convective storm, not just cyclones, but broadly convective storms in the region are changing in a similar way to what Andreas Sprain did for the MCS study, but looking into a very small convective storms in the region. Often we don't get these big mesoscale convective systems, so we had to look at smaller system. We use the same set of simulations, so 10 years present plus PGW, and employed a modified version of Andreas' algorithm to look for MCS, which I won't go through it, but it's basically looking into precipitation objects and then cloud objects that are very high, and then combining them to look for convective objects. Of course, the thresholds that they impose here are very different to those from MCS because it's a different kind of objects. But the idea is similar, is to look for these these areas we have both. We modified the code a little bit as well to make it more efficient, but essentially is very similar idea. Here I've got a set of the threshold that I use. So, for example, the area had to have at least 5 millimeters hour to consider a convective storm. That's a fairly agreed value, at least for this region, that when you get this amount of rain, is usually a convective storm. We have a size that should be 500 square kilometers, and some parameters in terms of the lifetime or the height of the clouds. And then also a little bit about the peak, which is what is the maximum within the storm to remove some storms that didn't produce strong rainfall rates. We played around with these. I will show just one experiment, but we played around with these parameters, and they essentially give the same results. It's just they include more small events, but essentially the big storms that were producing a lot of rainfall were all there. So it doesn't make a big difference. And I'll go through the plots I'll be using here because they're very busy. So here we condense a lot of information. We've got one variable. In this case, we've got the maximum wind speed on the y-axis. Then we have the maximum precipitation rate on the x-axis. Then the size of the storm in terms of the area covered by this is the size of the marker. And then the color is the total volume of rainfall within that. Obviously, as the area is bigger, the chances for that storm to hold more rainfall, more precipitable water is higher. So that's why we see bigger circles with purple colors. And then if we plot both in the same scatter plots, we can see what are the differences between the two. What are the differences between the two set of experiments? And this is for this region here. So this area that we put here. So a big area in the Western Mediterranean. And what we see, first of all, is a number of tracked events, which is a little number that we've got up there. So we have way less storms in the future runs than in the present run. And as I said, the only difference is the boundary condition, the PGW boundary conditions. We do see that they become bigger. We have a lot of events that are bigger in size and bigger in the amount of rain that, or precipitable water that they hold. But also we've got much higher precipitation rates from those events. So in the future, we've got events that we don't observe in the present runs. So I'll look into all the characteristics here. This is the same plots as before. We have larger, fewer storms, and more intense rainfall. And then wind intensity changes, which is in the vertical, is not as clear. We have some differences. If we look at the histograms, that is going to more intense value, but it's not as clear as the other changes. Then if we do the same, but we change the y-axis, and we look at the storm duration, and what we see is that there isn't really a change in the storm duration. We look here, and basically in the histogram is a clear image for these. Basically, they last about the same. We have a mix of lengths for a storm, but they're essentially the same. If we change it to the mean precipitable water, so not just the total precipitable water in the system, but the mean across the storm, what we see, obviously, the bigger system on average have less precipitable water because they are bigger, and so there are areas with less precipitable water. The small storm, they concentrate more the precipitable water, so they're higher in the scatter plot. And when we look at the difference between the two, that's very clear. That's the link to thermodynamical processes, so the CC scaling. And here is very clear that if we get a warmer environment, then we get this difference in the what moisture available for precipitation. Then we look the same with maximum CAPE, and again we've got an increase in the maximum CAPE. The histogram here is on the other side. Sorry about that. But we get lots of events with maximum CAPE with values that are not present in the current climate simulation. So that's one of the reasons why we get these more intense storms in the PGW simulation. Okay, so I think I'll conclude here. Well, as we saw here, for future storm changes, we've got fewer and larger systems, both in the size and the water volume, and more intense precipitation peaks. We see rates that in the PGW simulation that are not in the present round, they don't exist in the present rounds. We see clear changes in mean precipitation, in mean precipitable water, and maximum CAPE. And then when we look at winds, they're not so clear. There's slight changes in maximum wind, but no changes in duration. And so now what we're working is looking into individual storms, because this approach of using PGW allow us to look, at least for the very big storms, how they look into the future. So we can identify storms that are present both in the PGW and the present runs and compare one by one and see how they change. We have also looked at other seasons, for example, November, December, January, February, although it has a completely different dynamics, but the results are very similar. And then we're looking now into different subregions, because we suspect that some of these storms are moving across regions, so affecting different areas, mostly the northern and the southern Western Mediterranean in different ways. So that's all. Thank you very much.
All right, thanks, Daniel. Great stuff. So we have some time for any comments or questions. I'll open the floor. You ready, Jimmy?
So in the future runs, which scenario and decade were you using? It's like, how much warmer was it?
For the PGW?
PGW, yes.
Is the high emission scenario, is the SSP 585.
And which decade then, later in the century?
The end of the century. So we used 30 years. We compare 30 years with 30 years. Although these are 10 years, the climate change signal is doing 2017 to 2019 versus 30 years from the present. So 84 to 2014.
Okay.
So that's, yeah, we tried to get as close as we could to the present, and then looking into the end of the century.
And the other question was, in this future run, do you see medicanes, or have you looked for those?
We haven't looked medicanes, because the medicanes is something that came after all these studies, but it's something that we are planning to look when we're done with the convective storms, mostly looking at the, we know already from many studies that the frequency of medicanes is not expected to change. So what we're going to look is into the intensity of these events. Identify, we have a few medicanes happening in this period, so we're going to look into those in the future. And the advantage of medicanes is that they're big enough to be present in both the PGW and the present climate, so we can also compare one by one.
Okay.
Okay, any more? Rosie? This is why I was going to last.
Very interesting. Thank you for your talk. I have a question on the first part, on the medicanes. Could you explain a little bit in more detail how you tracked the source of water and how you attributed? How did you come up with the evaporation, for example?
Yeah, so it's a backtracking algorithm that we didn't get into how it worked. So we use it out of the box. It's a very robust and widely used backtracking algorithm, which is a WAM2 layers. You probably know about it. But it's basically about tracking and tracks in different layers where it comes from, but that's all I can say about it. We use it we wanted to use a tool that was easy enough to understand how much of the rainfall was coming from within our domain and outside. And this one was the easier. Talking to people in the field, they told us that it's quite a robust algorithm, but yeah, I can tell you the details of where we got it from if you're interested.
Okay. Yeah, I guess I'm not very clear how something can be attributed just to evaporation, because the fact that there is water, if you are backtracking just air parcels, for example, and there is evaporation, it doesn't mean that that is gonna rain out.
Yeah, so it's not really evaporation. I wouldn't say it's coming from that region, from the lowest level of the backtracking algorithm. actually there is 50% that is coming from elsewhere, and you're not able to track it back to the bottom layer. So there's some part of it that you miss it. If you go backwards or your domain is bigger, you end up going to the lower layer, and then you attribute it to that area where it goes to the lower layer. But it doesn't necessarily mean it's coming from evaporation. You translate it into evaporation because you assume if it's coming from the lower layer, it's reasonable that it's coming from evaporation, especially if you're of the ocean.
Okay, thanks.
Not very good at that. That's a kind of a technical question. With PGW, you kind of mentioned a little bit on it, but I'm curious whether PGW can actually include the storm track shifts because of the climate change, or that is something that is not taken into account. Of course, if you just change the humidity and temperature, that's out, but you're doing something more than just that?
That's a question that I always get, and I think everyone who works with PGW gets. It's hard to say how much. So you get the thermodynamical changes. That's clear. What's the percentage of the dynamical changes that you get? It's hard to determine because you modify winds as well in the boundary conditions. So somehow you displace a little bit the storm track, but obviously not enough to take into account all dynamical changes. Then the frequency of these events, large-scale events, you don't capture them at all. So let's say if you modify the frequency of NAO events, which are crucial for this area, if they are different in the future, then you don't get them in this.
Yeah, but climate modeling in principle should get you that, am I right? To some extent, if you trust climate.
Yeah, but you merge all climate models in one climate change signal.
Yeah, there you go.
And then when you look at the modifications, they're very small because the climate change signal, you look at the numbers are very small. So yeah, it's hard to say how much you take that into account.
Yeah. Would you do better if you just pick up one climate model and use that, kind of the one that is...
Yeah, you could do that, but the whole purpose of doing PGW in origin for us is that we couldn't afford to do actual, like proper climate projections because this is so demanding that we couldn't do that. And the go-to approach was, okay, let's merge all the climate models and assume that that's going to be better than just picking only one. If I had to pick individual models, I would go for many of them rather than just one, and then we can't just afford that. So, yeah. And then I'd like to say that I think the perspective here is different because what you want to look at is saying, we've got this storm, and that's when I was saying, look at it into individual storms. How does it change when we change climate change? So not just the frequency. I mentioned a little bit the frequency, but it's mostly how their characteristics change once you have the system in the area.
So I have another frequently asked question, possibly, about the first part. When you do the counterfactual changing sea surface temperatures, the atmosphere is unchanged, as I understand it.
In the first part?
At the current. So, but it seems unlikely that that would be true in a.
Yeah. So as I said, we did also the experiment, and in which we were changing the atmosphere as well. Okay. We tested that, and we did not as big ensemble as here because these were the production run. But when we were testing different approaches, we did that, and essentially we could see no difference between the one that was changing the atmosphere and the one that was changing the SST. There was, but in most cases it was really hard to see which one was which. So because the question that we wanted to answer in origin was the changes in the SST, we decided to go with this approach in which we only modify one parameter of the simulation. But if you modify the others, you get a very similar response.
Okay.
Okay, yeah. There's no one else. You get a second.
So what about this 7% per 1 degree temperature change? How that kind of classical climate change perspective for the Clausius-Clapeyron scaling fits into some of this work. I'm pretty sure you thought about some of that.
In the second part, in the part that
Well, the first and the second, because that's kind of...
yeah, we have a look into scaling. We haven't made the numbers for the scaling, so I cannot really comment on that because we're not sure. I'm not sure about the exact numbers, but I'm sure it will fit into the CC scaling, looking at the differences in the precipitable water that we saw.
Okay. Any final word from anyone? Anyone other than? Oh, Jimmy, you already had to go. Yeah.
I'll just say hydrology is next. You know, what does it do when it gets on the ground? And we've already talked about that. So, but yeah, that would be great to think about.
It makes lakes in the desert.
Well, right, but what does it do for infrastructure, and how do we prepare and be resilient to that?
Yeah, I didn't get your question, Andy. Sorry.
There isn't really a question; it's just a comment. Like,
Okay.
let's start thinking about infrastructure and resilience.
Okay. Well, thanks again, Daniel, and
Thanks to you.
yeah,
Thanks
you're
for
always
having me
welcome
here.
back.
Thank you.
And refreshments will still be around, so please hang around.